Looks like the feed's running. Let's start another Mythruna Development Weekly live stream. As always, we're going to be going over rivers. Hopefully this is the last one. I did make a lot of progress this week, and especially a lot of progress today, even after I announced the stream. I'd like to, again, thank my patrons. You guys really make a difference. Hopefully when we come down the way, there'll be some more benefits to being members. I look forward to that. So without further ado, let's go ahead and get started and see where we are. Let's move this down here. So, let's see, make sure the stream is running. Yep, okay, good. Okay, minimize that. So, this looks very similar to probably where we left last week, where I may have color coded things a little differently, but we had rivers laying out, and we used the costs to kind of find their way to the sea. Some things I changed are I made it so that if a body of water is too small, that doesn't count in the costs, and rivers won't try to go there. And that's a threshold that we can define. So that's why up here, this particular river skipped this little body of water because it was too small to have a river feed into. And that can happen in real life too. But I was pretty happy with how things turned out last week, and these rivers looked pretty good. And but then when I started looking at how it applies to a larger land mass, and let me go ahead and cause the map to regenerate so that these tiles up here get fixed. So when I started looking at this, that's obviously a lot of rivers, and some amount of culling has to happen because that's just crazy. And even wandering around the world, these rivers down here get super wide, and maybe I did have some of this working last week. At any rate, these rivers get super wide, 200 meters wide and stuff, which looks really cool. But when you have a 200 meter wide river here and another 200 meter wide river here, and you can almost see one from the other one, it gets a little crazy. So obviously these needed to be culled, and I wanted something. The color coding here, right? The red means that the river would have had to flow uphill there. Pink means it would have had to flow up a little bit, and so on. And then other colors are based on thickness. So by the time it's white, this is a pretty wide flowing river. And so I wanted to find an algorithm that would either correct the rivers or keep the best ones. And so what I settled on were a few things. One is I will score the parts of the river that are likely or more likely or less likely. So let's turn this view off. So we'll turn the drawing of the river data off, let that regenerate. And so we'll end up with a blank slate here for a second. And then over here, I have a separate draw rivers that lets me redraw it over and over and over again. So draw the paths true. Yeah, we're going to draw these. Use system scores false. Use path scores. Let's just see what this does. Okay, I've done something wrong. Draw parts, draw river paths, draw mouths. Oh, this whole file has been turned off. Okay. Okay, I still got my threshold set, so hold on. Draw river paths. So, okay, so this is draw everybody. So, the way this is set up is that, am I suppressing neighbors? That's not suppress neighbors. Okay, so we'll leave it all just kind of default scores. So the way this is set up is that um, each individual path will determine how uphill it goes and come up with a score. So let me talk about one of the things that helped me a lot was figuring out, after last week's presentation where I showed, my hand-generated side view, it occurred to me after I got off the live stream that I could have just exported data and loaded it directly into a spreadsheet. And so then that gives me like a real view of what things look like. In this case, the brown is terrain, and the blue is where I had plotted the river depth. So it's carving through the terrain in all these cases. And then because I had all the numbers and I could add my own columns and things, I generated a least squares regression, which gives me these, this slope and this intercept. So that's this yellow line is the least squares regression, which shows sort of the natural flow of the river. And so I thought maybe I could use that for scoring and things like that. I even went so far as to start plotting, where the branches are. So I have another view where, so I also looked at, calculating the mode and, averages and adjusted averages. So here was a surprising thing that I would not have learned I would have learned at great expense. I thought to myself, I said, these elevations along here tend to be pretty chaotic. So maybe if we sampled around there and came up with an average elevation, that would be less chaotic because, it would take into account of its neighbors. And so I actually sampled quite a wide area to create averages and included that in my spreadsheet. And that's what this green line is. And so for a minute, it was really surprising that the average was always higher than the actual, almost always higher than the actual terrain. And, so I scratched my head for a second and I'm like, well, of course, because when we plotted the rivers, we used the cost to the sea, and the cost to the sea, tried to take the lowest paths. So the river in any given place is going to have tried to take, the valleys. And so this was kind of confirming that my algorithm is working correctly because the averages were always more than the river. Now, obviously we don't like that chaos. But anyway, what I ended up with is, for each leg of the river, which may be several of these sample points, if I score it based on if it goes downhill or flat, add 1. If it goes uphill a little bit, don't add anything. Or if it goes uphill less than 45 degrees or whatever, don't add anything. If it goes uphill greater than 45 degrees, which none of this is going to show because each of these is 128 meters, and at any rate, so this is not really as steep as it looks. But if it goes up, greater than 45 angle, I subtract a value from the score. And if it goes uphill, but the flow of the river means that the width of the river would be about the same as the change in elevation. This especially happens down here because the river is very wide. And so down here, where, the river, we're only carving through 20 or 30 meters of, right, 128, we just barely go above 50, so maybe 20, 22 meters. The river itself by this point is almost 100 meters wide, so this little 20 meter high bump is just not going to matter. It's going to plow right through that, right? So it scores that based on the flow of the river at the time. So these guys get maybe like 90%, 75% of the score, because we'd rather not do this, but it's okay. If we still count that as a positive score if it flows through land that is only a little bit higher relative to its width. And so we come up with this, a score for each of these. Each of these means a branch. So the river branched here, branched here, and branched here, and on down. And so for each of these spans, we come up with a score. And I color code it. Really poor score is red. Medium to yellow is, orange to yellow is medium, and green is particularly high. And so these would be the river's probability. So I mean, ultimately, it's all going to be random, right? Even the rivers that are super unlikely may randomly happen anyway, because like I've talked about in previous live streams, lean into the randomness, right? You can always come up with a cool reason that some odd thing happened, but you can't make up for boring. If every river is completely predictable, that's boring. So, and if we want to see this picture a little clearer, I can start adding a thresholding in the algorithm that's in the loop that's drawing them. Where is that? It's these guys. So that's what I was doing here. If the probability score is less than 75%, then I can like eliminate them. And so these are just the rivers that would be better than 75%. So already we're starting to look more realistic. The other thing I wanted to do was, especially down in these cases, this is less than a day's travel between these two river mouths for these huge rivers. Well, this is pretty big, and this one is huge. I mean, this river system has a lot of water flowing through it. So here it's going to be maybe 100 meters wide, this river mouth. And if you're standing at this one in the far terrain, you'd still be able to see this other one over here. So what I did was I added an algorithm. Yeah, I am getting pretty excited because we're getting really close to having like rivers in the game. If a big river, I sort the rivers by river system size, so the longest path through this is like its size. And so if a river flows into a body of water and there are other rivers within a certain number of days travel that also flow into that body of water, I basically apply a negative probability to them. And so their probability will go down. I'm going to put this back so that we can see all of the rivers. So we've got this big long one that we want, and this one is probably going to suppress this shorter one. And so we'll put the suppressed neighbors code true. And so and so this river, by its nature, ended up projecting a negative probability down this one, which flowed down and made the whole river less likely. And it projects it down in a way where, in this case, maybe it was projecting it subtracted 1 from the probability of this river, which then would be 0.9% it subtracts from here, and 0.8% it subtracts from here, or 0.8 it subtracts from here, 80%, and so on, to the point where suddenly it's not really subtracting that much anymore. And the reason I did it that way is because if we filter back out the everything less than 75%, so we can see what rivers are actually expressed, you can see that the upstream of this river, some of those rivers might still form. Yeah, well, yeah. I mean, just running down these 128 meter wide rivers, I'm thinking, man, going up to the mountains and just like catching it from a stream and just letting it floating all the way down to the ocean, that would just be so cool. But so randomly, these rivers that up here might express as streams that flow into smaller rivers that end up in ponds and lakes. And so I have to make some pond and lake generation code. But I like this idea because even up in the mountains and stuff, you might get a river form and a lake mountain and so on and so forth. Like these guys, these might all flow up in. This is fairly high elevation, and so there might be a lake that forms here that all of these guys can flow into. So we get these random things. But looking back, this river generation is pretty good. As far as how far away the major rivers are. This river is 1, 2, 3, 4, 4.5, maybe 5 days travel if you were running all day. But ships could potentially go faster. So already you see some cool things can happen, right? We get maybe some mining towns up here in the mountains, and they can ship their product down to the sea. Maybe the only way to get, if there's special goods that get from the desert, the only way to get them to the sea is down here. Or, all of these trade routes bring goods and services, up to these towns that are in this dry area. Maybe that's good farmland. It just, the possibilities really open up. Yeah, and all these X's here are places where old rivers used to flow that we got rid of by thresholding them. So that's where we are, and I was just about to start basically actually applying, a random factor to these to start really deciding. If we set the score to 1, there's basically nothing that's 100% guaranteed. So, basically, if the score was 1, then we'd see a river here. There's nothing 100% guaranteed. So so if we randomize, even though we really like this big river, it might not end up actually expressing, and then one of the other neighbors might take over. Like this neighbor might take over because maybe this river didn't actually make it all the way to the shore. So that's what I'm going to start doing today on the live stream, is start applying the randomness to see sort of what we get rid of and what we keep, and removing some of the provisions I've put in that how the neighbors are suppressed, because neighbors should have been suppressed based only on whether a river actually generated or not, and I ended up just pushing probabilities, and so that'll change some of the math too. So this should get interesting. And I've already got it all booted up, so we can just start playing around. One thing that so one of the things I did last weekend and early this week that you can't really see in this picture, except for the fact that it generated all of this in about 20 seconds. We actually, when I first refreshed that river data file, that's what actually generates all these river paths, and then Draw Rivers just manipulates it and colors it and scores it in different ways, which allows that to be really fast. But all of these rivers generated for this 5x5 area take about 20 seconds, which is not bad. I picked a 5x5 area because I didn't know on average how long rivers would be, and the algorithm I've developed that will allow generating just around the player and then generating a little bit more and a little bit more is based on sort of a grid, and the assumption that no river that starts in that grid would end outside of that grid. Starts in the center of the grid would end outside of the grid. So you're just like the immediate cell you're trying to generate, and you want to make sure that you cover all rivers that go through that cell. Then how far out do you have to be? And I picked 5x5 because I didn't really know how long my rivers would be, and if there was a river that generated out here that would have flowed all the way into this cell, I need to know that. But probably it's going to be 3x3 based on just exploration here. But it was pretty encouraging that in 5x5 I could generate all that in 20 seconds. And so, that's pretty encouraging. Not great, right? We would want faster is better, but this would be the one-time generation when you first create a world. And there's certainly going to be other things that take time too. So if I can get that down, that's great. And the way this is 5x5, a 3x3. This is 25 cells. The 3x3 would only be 9 cells, so it's even, like about a third the amount of time. So that would be better. But I had to actually have rivers generate in order to see. Anyway, blah blah blah. I'm talking too much and not coding enough. So, but anyway, the thing is, when you're randomizing within a cell, you want predictability. So you have to figure out which random seed, because everybody's world should be the same, within some limitations. So usually that way that works is you encode, this particular grid cell, you get some value that's unique to that particular grid cell that, is based on math, and use that as the seed for your random number generator, because random number generators given the same seed will give you the same random numbers. And that way, if you started this world with the same seed, you'd get the same rivers I got, and so on. So it turns out that I can't just start pulling random numbers out of thin air. I have to pick how I want to generate them. And it gets a little tricky because this code's not real yet. It's not really generating the rivers for this cell. It's generating the rivers on a 5x5 grid. And so how do I decide within this cell whether to keep a river or not in a predictable way? And I think I'm going to end up going with a cache, or I'll build a map of random seeds, so to speak, so I can start a random session for each of these cells. And so if I find that there's a river mouth in here, I process them in some order that's predictable, and so on. In the real version, it will be a little different, but in this version, it'll at least be predictable each time I run the app. And actually, you know what? Given that, after all of that, I will instead just I already know the rivers are going to be in order, and I'm going to have some algorithm for determining tiles, so we'll just set it up. I think seed is okay, so I mean, after all I just said, in this app I'll just open one random session. They'll always be processed in order. That just means that when I bring this into the real game, we might end up with different rivers for this particular world because I'm generating a random seed up front, or starting a random seed up front. Anyway, so how I did what I've got so far is I created these river path structures, which for each of these, so when the rivers generated, they generated tributary down, or essentially independently. And the only way to know what a full river system was to traverse down from one of these river heads until you hit the mouth. And so I inverted that, and I created these river paths which take you from the mouth up to the first branch, and then each of these is a parent, and that goes up to the next branch, which each of these is a parent, and so on and so forth. So you end up with a river path, its parents. So the root river paths are all the mouths, and their parents, are the tributaries above them, and their tributaries above them, and their tributaries above them, and so on. So at any given level, you've got, basically the whole system up above you. And so that's done, and then you can apply penalties. You get an overall score where it basically aggregates all of the score of the various tributaries and things to give you an overall score, and that's used to calculate these probabilities that are being used to display this. Let's see. So I just wanted to kind of go over what I was doing. So this is building the river paths. This is still building the river paths. So I have a lot of debug code because that was not working great. And so once I've got all that, I can traverse the rivers, meaning it will traverse up these river paths from the root paths. And so I can do different things. In this case, this is where it's calculating the fitness scores. And so for each individual path, it calculates a score. So for this section, it'll calculate a score, and for this section, it'll calculate a score, and so on. And it does that based on the elevation, which I talked about before. And so if it's going downhill, delta's less than 0, less than or equal to 0. It's flatter downhill, regular flow, we add to the score. And then, if it's based on the flow and so on and so forth, we add different scores and so on. And then at the bottom, we normalize it to the length of the river, or the length of the scores we accumulated. So it'll be between 0 and 1. Speaking of, before I forget, applying a penalty, there may be a case where I want to I make sure that when I'm applying a penalty that the score can't go below 0, but I also need to make sure that the score can't go above 1. That screws up some other things, because I may apply negative penalties later to reinvigorate rivers that are unsuppressed. Anyway, so just save that real quick. Okay, so where was I? So that's where we scored the rivers. And so probably somewhere in here, this is where I draw. Oh no, I don't. Yeah, we draw the mouths. What am I doing here? I don't do anything here. This was a loop to, I think this was a debug loop. I was finding the regions. Oh yeah. No, so I see. I add a lot of debug code in here, but what this is doing is it's applying a river that's basically it's applying a penalty of 1 to rivers that are too big for a body of water. So for example, over here, this little body of water here, let me turn off the thresholding. So false. So you see there was like this huge river that would have flowed into this particular body of water. If I go back up here where we were applying this negative penalty, if I take that out, so this river, is quite green. It's very long. And by the time it got here with all of this up system, I mean, it's a huge river system. By the time it got to this little body of water, the width of the river was basically as wide as this body of water, or almost as wide. It looked ridiculous. And so wherever we find that, we've already calculated the regions for the world, and so we know where the oceans and the small water bodies are and stuff like that. And so if our river flow, half of our river flow is greater than the known area of a particular region, then we just apply a 1 penalty, which basically will subtract 1 from this part of the path and subtract 0.9 from this part of the path and 0.8 and so on all the way down. And so we'll see that go red, really, really red right here, dark red. And so these rivers might actually turn into something. So you could imagine there's a probability that these might express themselves and get generated and end up in a pond or a lake right here. So that's the way I did it that way, is for that reason, because water did want to flow this way. It's just ridiculous to have it end here. So we might actually make a bigger lake here based on how much water is flowing. Or, if probability says we don't generate anything here because we're going to not even generate these rivers. Anyway, you'll see as we branch up, we'll apply probabilities and randomness and get rid of things. So this is where we suppress the neighbors. I sort the rivers based on size. I come up with a two-day threshold. Two giant rivers should not flow into the same body of water if their mouths are closer than 2 days apart. And what that ends up with is sometimes you end up with things that are 4 days apart, like this and this, because, well, that's actually not. That's only 2 days, 3 days. At any rate, because this guy expressed and this guy was farther than 2 days away, and so he expressed, but then together they, suppressed all the rivers between them. So that's the way that works. And so that goes basically through, so here we're going through all of the sorted rivers. We remove them as we process them, longest to shortest, and then we go through all of the sorted rivers and check their distance. In reality, this would be some kind of grid-based index so that we didn't have to check every single one of them, but the amount of data we're dealing with, it doesn't take that long. So by the time we get done with this and we're here, we've already suppressed neighbors. We've got sort of a base probability, but the thing is, when we applied this, we assumed that this river would get generated, or that there was a probability that this river would get generated. There was a probability, and we used that to apply penalty to all these, but we don't know that this river is really going to be real. So we actually have to build in this decision right here. Like if we're going to even put this river in the world, then we know we need to suppress its neighbors. But if we already know we're not going to put this river in the world, then we don't need to do that. We're basically shorting this river. So I'm trying to think how best to loop that in. We know we want to randomize And so we'll basically randomize in longest to shortest order. Right, the easiest way would be, well, let's just see what happens if we take a, so I'll just call it dice, right? We'll take a dice roll, we'll get a random next double, okay? And if dice is less than the river overall score, get overall score, then we include it. So if it's greater than the overall score, like if we have a 90% chance and we roll, you know, so if we have a 90% chance and we roll a 95, we won't include the river. If we roll anything below 90, we will include the river. So we just continue here, and we want to suppress this river by applying a penalty. So actually, before we do that, whoops, let's back up a little bit and take a picture. Right, we want to be able to compare before and after results. Okay, so we'll take a picture, come over here, apply a penalty of 1, which means we're going to subtract 1 from its probabilities with diminishing effect. And let's move this so we can see it change. Alright, so let's hit Control S and see what happens. Brink. Alright, we've suppressed some rivers. Oh cool, we kept that one. And I'm going to change one other thing. So if we kept a river, we don't want to just apply its score. We'll apply a penalty of 1. Okay, so we'll do that. Alright, so now we take a screenshot. Come over here and compare our screenshots. Okay, so these were the raw probabilities with neighbors suppressed and so on. And then when we did a random on the at the river mouth level, we did a random and we got this guy. So we ended up mostly losing a river here, which allowed this shorter, smaller river to appear. We lost this river altogether up here, which is okay. It's just unfortunate. That was kind of a cool one. But you know, that's the problem with randomness. You get used to things, and you've got to be prepared to let them die because the random algorithm may decide they don't exist anymore. We lost some rivers up here, you know, but again, they might then create upstream rivers, and each one of these that goes away might allow another river to form. So we lost a couple over here. We lost some deeper. Oh, these emptied into smaller bodies of water, so we lost these guys. But it's not bad. Yeah. Okay. So here's one of the cases I was talking about. So we had a really long river system here that was quite high in probability, but we ended up deciding that we weren't going to generate it, and so it generated this one instead because we didn't end up suppressing this one like we would have because we didn't generate this river. But you end up with these smaller systems that might end up creating, you know, ponds and lakes and things. So, oops. And so it just changes the picture a little bit. Each of these upstream is random possibility that, you know, we might generate some like inland streams and so on. So let's put our threshold back, just so we can see without all the red what we ended up with. Yeah, so we've got, it actually didn't change the picture too much because these guys must have been pretty close to 100% probability. But that's pretty cool. And so now what we want to do is start thinking about the upstream guys and how we want to handle that. And I believe that's going to be a slightly separate pass. Let's put the, see everything again. So what I believe I want to happen is that in these cases where we didn't generate a river, I actually can mark it suppressed. So we decided not to generate a river, So I think it's suppressed. Suppress. That's true. Okay, what we should see is these guys that we decided we weren't going to include because their probability was so low. They should just disappear. That was not exactly what I expected. Let's see. Some of them worked, like this got rid of this. Well, okay, so the other thing is, there's another case where we apply a penalty of 1, and that is here. So we'll suppress the neighbor as well. And then we don't let it suppress anything else. We still might generate it. Okay, so yeah, so we lost all of these guys that were connected to the ocean because we didn't generate those rivers. But we want to add their children to kind of a queue to continue processing. And I think I want to process them in a different way. So I'm going to create a separate pending queue. And in Java, I think maybe I already have it pending. Nope. Yeah, so Java, you know, when you want a pending queue, and you don't want thread safety or any of that garbage, you create a linked list, right? Because you can remove things from the front. So pending for everything for any river that we process through this list, we will add its parents to the pending list. Pending add all river parents. Okay, so that means that any of those, so any of the upstream ones, we can decide to generate or not generate. And the reason I'm adding them to a separate list is because I think that the way we handle the non-mouth rivers will be different. Like here, when I decided that I was going to generate this river, I didn't change its score at all. Whereas upstream, if I decide, even this guy has a really low probability, as soon as I decide I want to generate this leg, I probably want to give back some score to the rivers above to make them slightly more likely, because otherwise you end up with these little spotty sections. So if you started to generate a river here, you want to make that slightly more likely. Maybe not as likely as it originally was, but or it would have been normally. Okay, anyway, so we add pending all the parents, and so by the time we get down here, by the time we get done with that loop, this loop, the while loop, we have a pending list. And so while not pending is empty, grab the river, okay, and same thing, basically we're going to process everything in kind of breadth first order, right? We process everything that was connected to a mouth, we'll process first, and then we'll process everything that was connected to that. And so we slowly move inland across the way, and because we'll have dealt with all of the first level first and all the second level next, and so on. So this will traverse all of those guys, and let's just see if it adds significantly to the time. No, it doesn't. So that traversed that whole graph. And so in each of these, we can decide, we roll our dice, we decide, right, do we include it? Is the overall score at this level? Do we include it? If we don't, we apply a penalty, we make it's downstream even less likely, although that's questionable. Maybe we don't want to apply a penalty in this case. So let's see what happens. Each level has the opportunity to get suppressed or not. Yeah, so see, we get random garbage. Let me take that out, and I'll take that out, and I'll So, um, so this is what the picture looked like before. Let me hit print screen. Okay. And so then if we put that, we suppress, basically if it didn't meet the dice roll, we suppress that level. But we don't do any kind of other processing to make the generated river more likely or anything. So we end up with this sort of random garbage. And if we take a screenshot of that, we'll see what this does to our... so this is what it, the fully hydrated river view looked like with all the scores and everything. And then when we randomly pruned, we end up with these random streams. That's not very fun. It's actually kind of cool that we did get some streams. Whoa, somebody's patinga-tinga-tinging me on Discord. Oh. Yeah, so anyway. She should be watching the Discord instead of, or she should watch the live stream instead of pinging me on Discord. Haha. Sathras and I go way back. She was one of the original JMonkey Engine people back in the day. I was gonna say on the live stream. Did our documentation for us and wrote the first JMonkey Engine book. Really nice person. Okay, so we want to kind of add some cohesion to this by, if we decide that we were going to keep this piece of river, add a little score back. So we're going to apply a negative penalty every time we don't suppress a river. So if we don't suppress the river, apply a penalty, but negative, maybe negative 0.5. So let me get rid of this because we want to see the live view. So yeah, let's take a screenshot of what this looks like and see how we fix it. Oh, actually, I just had a screenshot. Anyway, so let's apply it. Whoa! So that's bad. That didn't do what I wanted at all. So, I mean, it definitely increased the probability that we would minus 0.1 and see what happens. Okay, so I think the issue is that when we decided we wanted to keep something, yeah, well, first of all, yeah. First of all, there's a problem in that we're doing this even to the rivers that were generated, and so we're like wiping out any of the negative penalties they had in their little tributaries, and that's not right either. So this was close. Not applying a penalty is close. What if we apply a really teeny tiny negative penalty? Maybe we get something. Okay, so it improved it a little bit. Let's take a screenshot and see. You guys, I don't know if you guys might be thinking, what? I didn't see any change. There was a little bit, see, as I go back and forth. Maybe not as much as I thought, but. So that was with 0.001. Let's try 0.01. Okay. Take a screenshot of that. Okay, so we got some rivers back. That might be okay, actually. I'm a little disappointed. I'm a little disappointed in all of these red rivers. Hey, Jeremy. Thanks for joining. But let's mark some ponds, right? We've got, every time we decide we're going to apply one of these and our parent has been suppressed. So if the river parent if not, river parent suppressed. Okay, if the river, wait, no, if the child is suppressed. Sometimes I think backwards, but in this case, the parents are the tributaries and the child is the place we just came. So if we decided we were going to generate, this, but we didn't generate its child, we were a parent. The child is the one that leads towards the ocean or the body of water. That means that there needs to be a body of water generated here. And so we'll put a big X. X marks the spot. So let's see, V equals river dot path sub-zero loc. No, target loc. Wait. Mouth equals, oops, can't spell. So that's the river mouth. And if the river has a target, that's what we'll use, just in case. Mouth, oops, I'm losing the ability to type. Got 13 minutes left. Target not equal to null. Then mouth dot target dot loc, else mouth dot loc. So the location we'll do it is whatever the first item of the path is, which is the thing that goes uphill, and the target of that. So then markers dot add line, v dot add minus 100 50 minus 100. I'm sorry, I'm thinking about two different things at the same time here. And so in this case we'll add 100, color RGB cyan. So this would put a big slash wherever we generate. Yeah, so slash is where we need to generate ponds or lakes. In fact, let's go ahead and decide pond size. Let's just 100 and go back and change all these guys. Because I didn't fix this one yet, I can just do this. And so we want to flip this slash the other way. So now we draw a big X with our pond size. So all these little X's are places where we would generate little ponds. Some of them, it looks like a lot, but when you think about, each one of these hexagons is like a day's travel. So if we come in here, these little ponds, this would be a super small pond, right? A 128 meter long creek that drains into this little pond. So that one would be super small. This one would not be that big. You see the size of this little town here, which is not very little, right? We've got all those little buildings. So a little pond over here for that creek, and another pond over here, which this one's probably bigger. So anyway, so they're not as close as they look from this view. One second, I just got a text message I need to look at. Oh no, I didn't. I've got a notification that I need to turn off the notifications on. Okay, so let's make the size based on the flow. So say we want to be 10 times the river total flow. Except for we would want to recalculate the total flow. And we'll just do it for now. Pond size, river size, total flow. Whoa! Times 10 might be a little too big. Some of those ponds are giant. And so we can't even tell where they are. Yeah, see, this. So it seemingly makes no sense because because they still have the flow calculated from when they were full-size rivers. So there was all kinds of upstream crap, and so we can't do it this way. We can't render them here. We have to render that as part of regular rendering, and we have to use we can't render them here. We have to wait till all rivers are generated, and then we have to recalculate the total flow. I think that total flow, get max size. Let's see, how do I want to do this? So the total flow here is going to be, let's see, in river data we calculate the total flow by I'm going to try to spend the next 8 minutes getting the ponds to look right so you can see what's really going to be. So yeah, we just plus equal the wet, but we adjust wet. And I calculate the river size. So we fill in the flow based on these parameters and their wetness. Which is only slightly too bad. So min wet max wet visited, we don't need that. So we want to calculate the total flow of this particular path. Or double flow equals 0 for P path. So we calculate the wetness based on, it's a scale between min wet and max wet, and then we multiply it by min flow, max flow. So it's basically scaling whatever the wetness was between 2 and 10. We consider that to be between 1 and 6. It's rather arbitrary. I found that by trial and error. One day I'd like to unwrap the math on that, but not today. And so that wetness is our flow plus equals wet. Right? Let me see what I just removed. Well, let's look over here. Flow, total flow plus equals wet. Oh, I calculated wet just for the head. Yes, for each head I go down and okay, so we've got to redo that. Yeah. So this is not going to work because the total flow, I guess it can still work. Normally I calculate the flow by traversing all the way down, adding flow to every ledge of the river, checking the next tributary and doing the same thing. I can actually do it this way. I just got to include the flow from all the parents as well. So this is fine. This will calculate it at our level, but then I need to yeah, and so it will, if we're suppressed, then we're 0. Wait, no flow. where does 0, 0, 0? So, and so this is interesting because this will actually affect the coloring later. So anyway, the width of the river for even the ones we generate. So parent, we want to go through p parent and flow plus equals p dot calculate total flow. So we're basically recursing up the parents and returning flow. So we calculate the total flow. Will that do what I want? Yeah, because if any of these parents are suppressed, we'll stop there. Well, let's make sure my syntax is correct. Yep. Okay. And so, oh, where'd my rivers go? Oh, I took that out because I thought I had to do that different, right? And in a sense I do, because we need to. Yeah, right. I remember now. I'm back with us. We have to apply the penalty to all of the rivers before we can calculate their total flow. And so we'll calculate total flow where we draw them. And so double total flow equals, well, we'll only do it if the child is suppressed, meaning that we are expressing ourselves. So for river child, well, let's see if it has a child, and that child is suppressed, then we need to draw a pond, right? Because that's what we said. River child suppressed, we draw a pond, and the total flow then is whatever this river's calculate total flow is, and then we cut and paste this. And we see what happens. Uh-oh, bugs. That's what happens. No such property head for river path. That's true. Where are we complaining about that? 192? Nope. Higher up. There it is. 122. Aha. P dot wet. Okay. So that's still not right, I think. Well, first of all, we've got flow for places that we should not even be trying. Oh, we don't check if we're suppressed, so hold on. If so we do this earlier. If the river's suppressed, don't do anything. Okay, so that's at least got that. Okay, so this is a really tiny pond. It's a really big pond. And we got some ginormous. Okay, but this is not, I mean, basically it's a matter of scale. I think probably, why though? Oh, that's just a ginormous one is all. So we generated a ginormous one somewhere around here, but we can't tell where because it's too big. So let's just try taking the square root. It's a quick way to pull things into, yeah, okay. Yeah. So if you ever have to make geometrically increasing numbers, smaller, square root can be a good way because it, it geometrically reduces them again. This, see, this seems wrong. These seem okay. This seems like it should have been bigger than this one. So I've got some debugging to do. Yeah, this guy should have been huge. But, we're really close, and I'm certainly going to resolve this probably tonight, right? That's some debugging on my part, and we're at our hour mark. If you guys have any questions before I quit for the night, we're getting really close, right? I was actually going to I hope to finish with this early enough that we could start looking at what pond generation is going to look like, but I think I'll probably just end up doing that this weekend. And I imagine you guys are probably sick of talking about rivers, but you'll see why it's important when we start to get the town generation and so on and so forth. So I'll finish river generation, at least enough to rough lay out the rivers, because that'll be enough for plotting towns and things. And it's enough to test. And then I'll probably get caves in, because caves should really be generated before the rivers in the sequence of things, because rivers might flow into caves and things, and we need to know that. And then I'll start working on town generation. So we might get to town generation by next live stream next week. Anyway, thanks for joining me. Give it a last beat for questions before I start bringing up the closing title cards. Share with your friends. The more people we can get liking these videos, maybe the more people can see them, and the more buzz we can generate for Mythruna. That'd be cool. Though pretty soon we'll get to a public release, and hopefully the buzz will come up soon. So thanks for joining me, and I will catch you guys online and so on. Join the Discord if you're not already on the Discord, and I will see you guys next time. Thanks.